morning. Glad to see you all here today. I'm Joanne Bundy, and the Planning Committee joins me in welcoming you to the bucket courses. If you will silence your cell phone and turn on your tea coil, we have a couple of items of business to talk about this morning before we begin class. First of all, you will see the sign-up for the registration sheets that are on your table. And those are for Dr. J.R. Paulson's course, which begins 3 weeks from today. We expect a sold-out crowd, and we want to give all of you first chance to sign up for his course. Now, Jim will also be sending out an email so that for people who are not here, or if you prefer to wait for the email, you can register then as well. So that's what that is for, and you can just put JR on the top line. We will know what you mean. 2 weeks from today, we have Open Wednesday, and we have a really interesting topic for you and a wonderful lecturer. Dan Kaiser, who is Joe Rosenfield Professor of History Emeritus, will be talking about the rise and fall of Grinnell Giant. Remember. And Dan is kind enough to be here to give you a little preview of what his lecture will be. Please welcome Dan Kaiser.
Good morning, and thanks for giving me a chance to talk about this. I should say, unless we get a snowstorm, right? It's not ruled out of the realm of possibility yet. Mike was kind enough to put this picture up. This is the Ricker House, which many of you may know very well. I walk by it since we moved to Manor Drive. I walk by it several times a day for the past 15 years or so, and I think about it a lot. And the more I went by it, the more I wondered about the people who had been responsible for putting it up and what happened to them. Because although people call it Ricker House, we don't know very much about Benjamin Jewett Ricker, who was the man who was responsible for having this house built in 1911, finished in 1912. And it's B.J. Ricker that I want to tell you about. I'll just give you a few moments here. I think of it as a kind of a morality tale. B.J. Ricker was the 9th of 10 children born to Edwin and Clara Ricker, who moved to Grinnell in 1867. Ricker was the first one born in Grinnell, 1868, and he spent most of his life here. Went to Grinnell schools, graduated from Grinnell College. In 1891, as a graduate, he went to California, apparently made some money real quickly, came back to town in 1895 and bought into the Grinnell Glove Company, which his brothers-in-law, Andrew McIntosh and David Morrison, were running and operating. So he got in on the ground floor and actually made a big deal out of it and contributed important things to it. He got patents for several designs, including a glove that made most sales for the factory. And he got rich very quickly and became influential. He was a Grinnell councilman, then was a director of the Merchants National Bank. His building still stands down here in the corner of 4th and Broad. Became a director, a trustee for Grinnell College, and through the at least until around 1920, was a very influential person in town. But then things went straight downhill. And what people don't know very much about B.J. Ricker is he kind of went bust. And he fled town in 1925, leaving his house behind unsold. He tried to sell it for about half what it had cost to build it, hadn't succeeded with that. He owed that much on the house, owed a lot of money to the glove company, something over $300,000, and was also part of the default of the bank here, which went bust in 1924. So in 1925, B.J. Ricker left for California and started a whole new life. And we'll have a few things to say about that too. But it's largely about the family, not the house, although I love this house, and I spend a lot of time just dreaming about it. But people who were responsible for building it will have a good time, I think, talking about them and what their lives added up to. So I hope that you can make it, assuming we don't get a big snowstorm, right? Thank you very much.
Thank you, Dan. Now that's 2 weeks from today. And as usual with the Open Wednesday, there is no pre-registration and no tuition. But I advise you to arrive early that day. And now we will start back to our class with Mike Guenther, talking about society, science and society from Darwin to, no, from Newton to Darwin. I'm not doing well this morning, but here is Professor Mike Guenther.
It is such a pretty house. And I love seeing it there with the daffodils all in spring. All right, so today we're going to talk about classification. The first lecture we did, our class was about experimentation and how that became a hallmark of modern science, and then we talked about mathematics and trying to turn nature into numbers. And today we're going to talk about what I think is certainly one of the most important aspects of modern science, this drive, this I call it kind of impulse to kind of provide order to the world, to classify. And so we'll talk a fair amount. I have a quote here from Linnaeus. We'll talk about Linnaeus and his famous system and in botany. But one of the things I hope to kind of impress upon you, and I think is really interesting, is just how much of this technique spread to almost every field of natural science, social science, even the humanities. The idea was if you wanted to really understand things, what this kind of quote gets at, if you want to get a true idea of objects, you first have to classify them methodically, give them meaningful names, kind of understand their relationship, understand their essence. And that's what classification was all about. There used to be a quip that God created nature, but it wasn't until Linnaeus that someone finally gave it order. Here, and Linnaeus actually, as you see here, he kind of, in some ways, adopted, embraced that role, almost like an Adam in Genesis, giving names to everything. We'll talk about all these different founders of science who use classification as their kind of first technique. So I wanted to talk about the weather first, though, before we get into botany, just to kind of give us a sense of the range of what it means to classify, why and how people do it. Especially since it's April here, we're watching clouds roll in and out. I thought, what better thing than to start with an individual named Luke Howard. And his attempt to create a system, a nomenclature, and a system for understanding clouds and the weather that we still use today. He's the person who gave us the terms cumulus, cirrus, stratus, nimbus, all the kinds of terms we use today here. And it's kind of fascinating. He wrote an essay when he was in his early 20s called The Essay on the Modification of Clouds, in which he proposed this system. He thought of himself kind of as the Linnaeus of meteorology, someone who's going to give order, give names to nature. He himself was, I think, like the ninth son, a little bit like the Bricker family, the ninth son of a Quaker family. He inherited the business of pharmacology, so he made drugs for a living. So I think that's kind of important because he was someone who would have been trained in medicine, botanical plants. He would have been someone used to using nomenclature to identify plants and drugs. And he thought, why not apply that to the clouds? But when he wrote his essay, he kind of understood what he was doing was a bit audacious because nothing seems more idiosyncratic than a cloud, right? I mean, children, everyone loves looking at clouds. You can imagine what they look like. Every cloud is unique, almost maybe like a snowflake. It's got its own character and whatnot. But he thought, no, actually, I think we can systematically understand that there's actually a structure behind clouds, that they can fall into categories and camps, and that we can figure out how to do this. And so I have here some of these. He did these kind of interesting watercolors, but also some different engravings in his essays. And he was widely popular and read. This was reprinted in all kinds of magazines. The cirrus clouds, the highest clouds, cumulus from Latin, the big puffy. Cumulus is a lump in Latin here. Stratus, the very low line. In fact, he developed this kind of, like a lot of these people at the time, he emphasized you've got to have Latin nomenclature, which I think is kind of interesting. Almost every science decided one of the things we need to do is get rid of vernacular language because it has metaphors, it's rich with meaning, it has connotations, and we don't want that in science. We want to be able to communicate to everyone around the world. We want to develop new Latin terms so we wipe away all those, what they would say is superstition, and kind of start with a clean slate. And we'll talk a little bit why that was kind of problematic in some ways. But, so he insisted, let's have a Latin nomenclature, let's divide all the clouds up into these three categories here based on how high they are and based on their structure. So the very highest clouds are the cirrus, they're way up in the atmosphere, and then cumulus. Let me just show you a kind of modern diagram just to give you some sense of the different types. So we have the cirrus clouds at the very highest. And what he did is he developed a system where you could combine the names when the structures were shared here. That's why it's called a polynomial system here. So you have, when you have very high clouds that are kind of puffy, you have cirrocumulus. When there's a kind of haze, stratus means flat, so when you have high-level clouds that have haze and you have these beautiful halos, sometimes if you'll notice, especially in the winter with ice crystals, you'll see the sun has these kind of rings around them. All of these kinds of things. This is the cloud that we do not like to see here in Iowa in April, right? One of the things that's interesting is that he starts to develop, using this nomenclature, he starts to study the sky and starts to realize I can start to predict when thunderstorms will happen or when rain will happen based on, again, not seeing the sky as every cloud is an individual kind of entity, that there's randomness behind it, but instead saying that there's a deep pattern. Nature must operate in an orderly way. So if I can understand the structure of the clouds and the sequence, the way they move into the sky, the way they interact with one each I can probably understand the weather here. So this is one of his drawings in his essay where he talks about how you get one of these cumulonimbus clouds, which are thunderstorm clouds. How do they form? And how do you predict it here? And so he starts to show the way the different structures of clouds interact. And I'm not going to get into all the details here, but for contemporaries, it's quite remarkable, this idea that the weather, which seems one of the most unpredictable things in the world. There's also something we talk about all the time. That science could, just by using some Latin names, by using some classifications, by starting to break down the weather into categories and carefully studying their sequence, that it could somehow start to offer new understandings of the sky itself. And one of the things that he does that's kind of interesting is he develops a system of notation. So every cloud has to have a little symbol. Here, what he wants is he wants every weather watcher around the world to use these symbols. So now you can take records of meteorology from Sri Lanka, or from Canada, or from England, or from Buenos Aires, anywhere in the world. If people are using this system, all of that information now becomes interchangeable, right? They're using the same names, they're using the same categories, they're even using the same kind of system of notation. So this idea that now you can accumulate knowledge from all around the world and study it because it's able to be integrated. It's not apples and oranges anymore, right? It's kind of integrated. That's one of the keys to the idea of classification. That you can make all knowledge kind of interchangeable. And lest we just think that that was something exciting for scientists, I think one of the more interesting things is how much artists, poets, popular culture embraced Luke Howard's kind of mission. So I have up here this is John Constable. He's one of the kind of famous British landscape painters of the late 18th, early 19th century. He did these really beautiful, I encourage you to look online, studies of clouds throughout his life. Mostly after he read Luke Howard. I'm not going to say that artists and poets weren't interested in clouds before. There's just an explosion of interest after Luke Howard writes in 1800 and proposes this system. Goethe writes a series of poems about clouds. Even Wordsworth's famous poem about daffodils, where he imagines he's a cloud looking down. A lot of the imagination is kind of set on fire by this new system and by the idea that you can study the cloud with an appreciative eye, that you can appreciate the deep order and symmetry in nature. They're not just a heap of clouds anymore, but there's a deep pattern that reveals, in some ways, the hand of the creator himself, that there's kind of order behind nature. So Constable does these paintings, and apparently when I've talked to meteorologists, they say that starting in the 19th century, you can actually use paintings. They become so accurate that you can kind of use them to understand the weather patterns of the time. So they're not just puffy clouds that look pretty, that they're actually structured in a way that scientists see as kind of realistic. Here's one of his paintings that's at the British Museum. I love one reviewer said that when he saw this painting, he wanted to grab his umbrella. It just conveyed such a sense of wetness and kind of thing. But I just wanted to turn to an American example too. If any of you are fans of the Hudson River School of Paintings here, you could look at Albert Bierstadt, Thomas Cole. But I picked one of my favorite paintings from Frederick Church, Twilight of the Wilderness here. It has this kind of beautiful kind of layering of clouds. He's now looking at the color as well. But again, science and art kind of merge in really interesting ways around this issue. And also, this is another kind of famous painting by Thomas Moran, The Chasm of the Colorado. I believe this hangs in the U.S. Capitol. I think the Congress paid for this. They were quite impressed with it. But in a similar way, when you start to look at paintings of the West in America or other parts of the world, you see that all of a sudden there's intense geological detail in the paintings. There's another place where you see classification at work is in geology, the study of rock layers and stuff. So it goes from being, if you look at paintings of mountains in, say, the 1700s and compare them to the mid-1900s, you'll just see an explosion of level of carefully planned detail in rock formation. So kind of artists, like I said, artists, poets, writers, they're all kind of interested in what they're seeing as the hidden order of nature that's being exposed in these different kind of earth sciences here. Now, let me just take one other example. I think this one's kind of interesting because it shows the range of how classification can work. I want to talk a little bit about the Herschel family here. So we have the father, William Herschel, who some may or may not have heard of. He was a famous astronomer, originally from Germany, but he spends most of his career and life in England. He's made a royal astronomer. He also has a large family of children who are very talented and kind of make names for themselves here. But I want to focus especially on his son, William James Herschel, kind of Herschel the Younger. So these father and son are really interesting because they both use taxonomy in very different fields that show kind of the range of this technique. So I want to start with the father here. He discovers the only planet discovered in the 18th century, Uranus. He kind of develops these star catalogs. He's a prolific astronomer and a famous one, and a musical composer. He's got kind of all these, it's a polymath, all these interests. One of the things he's famous for is building better instruments. He has this enormous telescope he builds. It's about 40 feet long. He has this huge reflecting telescope, which allows him to see these planets. But what I want to talk about today, which I think is also interesting, is a lot of his actual impact on astronomy was not his better telescopes or his trained eye, but his ability to, as he said, reform astronomy by bringing classification to it. Okay, they've counted 9,000 stars. Are all stars the same, or are they different? It's a basic kind of question. How can we organize or group stars? And it's one that hadn't really been asked until Herschel. So he developed this whole system of stellar classification. For nebula, this is an image from one of his works about galaxies. Let's start organizing galaxies into different categories here. And in fact, his scheme is still used today. It was modified by Hubble, who the telescope is named after in the early 20th century. But again, he laid the structural foundation for modern astronomy by figuring out. Again, inspired a little bit by Linnaeus, but let's organize these into 5 different groups or categories here. Here's an example, another print of him doing it with nebulae. Here, these are like kind of clusters of stars that are very hard to see with the eye. They just look like kind of faint smudges on the telescope. But he started very carefully saying, well, okay, I'm going to divide their luminosity into 5 ranks. And even their smudginess, he has these different categories, with Milky being the bottom, like the Milky Way, and I can't remember what the names are for the top, but he develops all these kinds of categories here. And like I said, has a really deep understanding, starts to develop, based on this classification and the developments with the discovery of light, people start to tell how hot stars are, and also they start to tell when they might have been made, how far they're away. So what starts off as just a kind of useful exercise, maybe like organizing books alphabetically, right? Let's just kind of start organizing. You end up starting to get insights as you start to group stars together. Why are these stars together? What does their light tell us about it? What is their kind of visual aspects? His son did not go into natural science, but he was trained. His father kind of wanted him to work in astronomy. So he had a good training in classification, and he's really the progenitor of fingerprints, for better or for worse, which I think is very interesting, right? So he actually, William John Herschel ends up becoming a civil officer in the British Empire in India, and he ends up being in India in the mid-19th century, working in Bengal, and he's been noticing that when he leaves, everyone knew that you could leave kind of prints on items, but he makes a kind of systematic study where he studies his prints over the course of 25 years and notices that they don't change at all. People thought the prints probably, because skin cells shed, that they would change, but he discovers that they stay the same the whole time. So again, he just says, well, let me can I classify fingerprints? Is there any way I can organize them into an orderly way, the way Linnaeus did with the botanical world, or the way my father did with stars? So he starts developing these categories that are still used today, and they get perfected by Francis Galton and some people later in the 19th century. But arches, whorls, tented arch, you can see these kind of categories here. And then within each of them, he can kind of break it down and say, okay, within an arch, what are the distinguishing features? What's the next category of classification? So I think today we use like a 10-point system or something like that. But again, this idea that you just, in some ways, part of the excitement about classification in the 19th century is that there seems to be, like I said, hidden order in nature. Who would have known that every single person has a different fingerprint? You think Galton, who's a great statistician, estimates that the chance is 1 in 64 billion that a person will have the same fingerprints, is kind of, because he's using kind of advanced statistics here. There's still some debate about exactly that number, but in general, this idea that, again, classification, you can use it on the stars, you can use it on almost anything here. This idea that it's intensely useful, lets you communicate with other people, but also might reveal, like I said, hidden patterns in nature that were quite unexpected here. So let me just say a little bit of word about, let's go back in time. Where did this impulse come from? Obviously, some people were trying to copy Linnaeus. Where did Linnaeus get his ideas? Why did classifying, which has existed throughout human history, and all people classify the world into different names and categories, but why did it become part of what we call modern science and become such a part of the kind of scientific method? And so I think the real place to begin is to go back to the 17th century, to the scientific revolution, and to look at a strain of thought that wasn't tied to experiments or math, but was tied to this figure, John Wilkins, and this idea that we needed to reform language, and we needed to reform all our categories of thought if we were ever going to get a clear idea of nature. Yeah. And so his idea was basically we needed to get rid of the English language, the French language, all of these. We needed a philosophical language, one in which every word captured the category of the item it was describing, not just a name for it, if that makes sense here. So the idea is that we're going to create a language in which we're going to create 40 genera, which is just the plural for genus. So 40 classes of things here. And then the first two letters of each word are going to reflect that category that it's in. Then each genus we're going to divide into what we call differences, which you get one letter after that, right? I'll give you an example here because this is very abstract. But differences are divided into species here. And notice the language, if any of you are familiar with botany, or just in general, species, genus. Differences is, not quite what you expect, it's not order. But in general, Wilkins starts to kind of develop this idea that even language itself can have a taxonomy, can have a structured system. So let me give you an example here. What would a flame be in Wilkins' language here, right? So one of the genuses, one of the categories is an element, like the most basic fundamental, an element, right? So that would be DE. And then the first of the elements, fire, is DEB. So any word that has anything to do with fire is going to start with DEB. And then the visible part of the fire, a flame, has an A added to it. So Deva. Here. So, and it seems a little strange. You can imagine that this did not actually go that far. People weren't really excited about learning a new language here. But the idea is quite interesting, which is, in many ways, there's no logical reason why we call a lamp a lamp. It's just a name that it's a social convention, attaching a set of syllables to an item. Here he's saying we need to actually categorize it so that language tells us exactly what it is and how it's related to the elements, the element of fire and whatnot. So it's a very interesting prospect, even if it doesn't go too far. One of my favorite examples he has in the book is, let me show you what the Apostolic Creed would look like in his language. So he has his own system of characters as well, because he wants to get away from the alphabet here. So he develops this kind of system of writing here. So this is what it would look like. And you will find, if you look in the 17th century, well into the early 18th century, there were some people that used this system, scientists. And when I worked at the Royal Society in London, in the archives, I came across this piece by Robert Hooke, which is a description to the Royal Society of a spring watch mechanism. Here, and you'll see that it's written in Wilkins' universal character here. So, which means, of course, that I skipped over this in the archive because I don't know how to read that. There are some scholars that are trained on how to read the universal character. But, and this idea that would come back in the 18th century, the 19th century, there were different people who would propose something similar. And eventually, too, you have people using kind of symbolic logic, using the language of math to kind of do something like this here. So we have these kind of deep philosophic roots. And this made a big impression on people in all fields, whether it's botany or chemistry. In fact, I do think it's really interesting. The term that's used is called systematics, if you're ever reading in the 18th to 19th century here, or classification. But it's basically the same idea, which is trying to kind of discover the hidden structure that bounds together a system, whether that be a system of language, a system of plants, a system of diseases. This is one of the more interesting ones. Medicine starts to take on the idea of classification. Let's start classifying all diseases, which is a really controversial issue because people had argued that every disease is idiosyncratic. It's particular to the environment, to the nature of the person and the body. You can't create a category of a disease. But certain, kind of reformers push this idea, and bore some fruit. By grouping together different diseases, you could discover that some diseases were communicated in a similar way as opposed to others. So there was some insight that was gained here. This still exists even today. I think it's always fascinating that we have an international convention, so there's only, if you take the issue of death, there's only 27 ways to die in this world. They're all officially categorized because they want to create statistics. They want to know how many people die of cardiovascular disease, how many people die of other features. And so one of the things that's very interesting is if you want, and so this lecture in some ways ties back a little bit to the quantification lecture. If you really want to count numbers, if you want to develop statistics, you need to have categories and a classificatory scheme to make sense. So, yeah.
Well, we all know that the suffix ology means the study of whatever. How in the world did the greatest of all sciences, chemistry and physics, get by without the suffix ology?
Okay.
I mean, that's a glaring error.
A glaring error in the naming of it? Yeah. So the question is, when you look at words from the time period, you see the kind of the Greek ology attached to it, which is the study of it. So he's asking, why is physics and chemistry bucking that trend? Like the leading sciences of the day, why don't they end? Why isn't physicology or something?
Were they just
chemology.
so powerful and arrogant that they said, we're not going to go with it?
Are they powerful and arrogant and buck the trend? Well, actually there were an attempt by people to classify knowledge itself and to come up with new names, that they wanted to redo the naming of these different disciplines. And sometimes you'll see, whether it's like meteorology or other fields, that one of the first steps to announce that you're being scientific and that you're stepping away from popular tradition is to develop a new name, gnoseology. Organization of fish is ichthyology or something like that. I might be mispronouncing that. But yeah, so there's that attempt. These are older categories. I don't know why Aristotle calls it physics as opposed to some other physiology.
Or physic.
Or physic, yeah. I don't remember people at the time also complaining that they were arrogant for not having theology. But it's a good question. I mean, what is in a name in these different branches here? So yeah, I don't have a particular, although most of the sub-disciplines within it do adopt this kind of terminology here. And so you have in different fields. Chemistry is another really good example. Mendeleev and the development. Well, first you have Lavoisier and people deciding, okay, we've got all of these different chemical compounds and subjects. How do we create some order out of them? Can we create categories? And there have been categories of salts and acids and things. But they reformed the name. They insisted on Latin nomenclature, and they started to organize them much more methodically. Like one of the things you'll see is everyone talks about, I'm going to reform my field. And by reform, they usually mean I'm bringing in Latin nomenclature, I'm bringing in systematic classification. We're going to kind of organize things in particular ways. And so Lavoisier starts that. And then you have, building off of that, the idea of let's build a chart, the periodic chart. Let's organize the elements visually according to principles of atomic weight, according to how they interact with other atoms. And then they start to discover really interesting things. There's gaps in the chart. And so they purposely decide in the 1860s to leave those gaps there because they predict that they will find elements that fit those gaps. So one of the things that comes out of sometimes from classification is a predictive power. If there's something missing in the chain that you're studying, the categories, there's a good chance that it exists out there and you just haven't found it. So people start looking for that here. So you see that in chemistry, same thing in physics, different fields. So yeah, almost all these different mathematics, geology, probably any field of human knowledge during what we often call kind of the golden age of classification, so the 18th and 19th centuries. Almost any field is going to be interested in using these kinds of techniques. So let me though say a word about the person who was kind of the superstar of classification, the person who in some ways kind of put it on the map for a broader public, which is Linnaeus. And botany becomes the prime example of a field that is transformed from being a kind of, I don't want to say backward science, but during the height of the scientific revolution when astronomy and physics are making breakthroughs, discovering laws left and right, botany seems to be kind of languishing. And so it's up to Linnaeus and a group of early 18th century scientists to kind of propose radical reform and change. And they're going to do it through not so much mathematics or even experiment. They're going to use this technique of classification here. So at the heart of it is a system that he develops of kind of binomial classification, in which basically, one thing to emphasize is it's an artificial system. Linnaeus, although he wants to get at God's plan of the universe, which is ultimately what a lot of classification is about getting to. What is the secret order of nature? And in the 18th century, that's especially seen as God's order. You know? So how do you get at that? He's not exactly sure because it's overwhelming. One of the things to emphasize is that the 18th century, it's not an accident that an age that's obsessed with order and classification is also an age that has an explosion of knowledge, information, and material coming from around the world. So Linnaeus and other botanists are seeing tens of thousands of new plants, animals, minerals, drugs. They're coming in from all around the world during the first great age of imperialism. So Linnaeus, even though he's from Sweden, he does all of his research in Holland, which is important because Holland is an imperial power. Holland has the botanical gardens, it has the global commercial networks to bring in all this material. So in the face of all of that overwhelming material, how do you provide order? So he developed a very clever, although acknowledged, artificial system. So let me just focus on plants. He says we can actually divide plants into 24 categories based on the flowering part of the plant, how many stamen it has, how many pollen-producing stamen. So you can have a category, if it's one stamen, it's a, I don't remember the term here, monodria, duodadria. I think they're kind of complicated Latin terms, but 2 stamens, 3 stamens, then there's different categories of a plant with 6 stamens, 4 of which are long, 2 of which are short. Yeah. Now, the brilliance of it is that it's so easy to use that if you take about 40, 50 minutes to learn it, any novice can identify any new plant, no matter how kind of strange it is, by the system, and they can give it, and under this kind of system he creates, they're given the right to name it here. So you have this kind of binomial naming system in which there's a genus, a kind of class of related flowering plants here. There's 24 of these. And then you have a species within it here. So it's a very easy to use system, but it's also, as he acknowledged, it's a very artificial system. So you get plants grouped together that don't seem to share a lot in common, right? So what does a gardenia have in common with a cactus, right? Not a lot. But it turns out that they're in a similar, I might be wrong about this, but there's other examples. But you can get plants in the same genus, the same categories or classes that really don't seem to belong together, don't seem to share much in common. So that's one of the downsides of the system. But the popular side, or the upside, is that it's so effective and convenient. And it gets rid of one of the big problems, which is every country had different names, different scientists had different names for plants. It creates a very useful kind of way of organizing. And I think it's very important. It invites people to participate in botany. People of all ages, of all sexes, of all classes start to get really interested in botany because it's the most accessible of all sciences. And you can name something, you have something named after you. It becomes a very participatory kind of science. Yeah.
Why did people in Holland and England or wherever all use Latin as the base, excuse me, base for their naming their genus and all that stuff?
Okay, yeah. The question is, why did people in Holland, England, France, why did they use Latin to name this here? And so it has to do with kind of the cultural background that Latin was the language of educated classes. That people would learn it at kind of grammar school level. And so it was the one language you could use, although French always wanted French to be that as well, the lingua franca. But, so there's a little bit of debate in there. And sometimes you would see a classificatory scheme be proposed that would actually lose out because it was based on the vernacular language. So there were some French schemes by people in the 18th century which seemed equally useful, but because they were couched in French, other scientists had a hard time reading it, or they didn't like to use it, or whatnot. So Latin was important because everyone used it, and it wasn't tied to kind of nationalism. And also the resonance of it wasn't as powerful. So names didn't convey emotional significance or things like that. Being a dead language was seen as kind of useful for scientists, because they wanted to strip away what they saw as, again, bias or superstition. So Latin became very popular for that. It eventually gets, works by people like Linnaeus get translated into these other languages, Dutch, French, stuff like that. But they continue to use Latin as the nomenclature. And there are a couple sciences that use some other system like Greek or whatever. But in general, if you study classification across all the sciences, including the social sciences, they tend to use Latin a lot here. So I've got a couple more minutes before the break, and I just kind of want to finish out. So Linnaeus starts off the Enlightenment by developing this very useful system that organizes all of the world and invites people to participate in ways that are seen as very pious too, because they're kind of mapping out God's plan by kind of creating order in the universe. But he does hope that eventually the categories will be shifted around a bit, that these systems can be changed and that it will become more natural. So he's fully hoping that maybe 100 years later that they might change the categories a bit in order to group things the way God intended them rather than the way that's easy for us to count stamens. And the person who kind of seems to succeed in doing that is a French person, Cuvier. There's another person named Jussieu and some others. But what they do is they start to turn inward. They start to use anatomy, the scalpel. And they start to dissect plants and animals very intensely and very systematically. And they start to kind of say, well, let's not organize things just by counting stamens. Let's organize them by the key functions of animals. So regeneration, respiration, digestion. They start making a kind of a hierarchy. These are the most important functions. These are the next most important. And let's group animals together that share a physiology and anatomy that are shared in those functions here. So we get interesting things like whales being in the same class as eventually what will become mammals, right? Because a whale lives in the sea, it looks like a fish in many ways, but if you look at its respiration, the way it regenerates, feeding of its young, things like that, it's seen as having more in common. I know it's very counterintuitive. You can imagine what people in the 18th century thought. Bats. Bats are no longer in the family of birds. Instead, they're put together in this new classification called mammals. And I'll talk a little bit after the break about why mammals were created as a category and why they were controversial. But this idea that, okay, the world on its surface is this glittering kaleidoscope of all these different creatures and animals and plants. But if you carefully start to look inside and do what they call morphology, which is kind of mapping out the structural patterns within the anatomy of plants or animals, you start to see much more of God's plan at work, they start to argue. It's much more orderly. You can start to organize creatures into these really interesting patterns that tell us a lot about nature. Here, one of my favorite examples is that Cuvier would always, and he did really he was a very good publicity person for his scheme. And so he used to always have a challenge. Give me a tooth, and I will tell you what the animal is. Yeah, that's all I need is a tooth. One tooth. And so people would send him different teeth. Jefferson sent him a mastodon's tooth, other people. But, and it seems a little strange, but you can imagine for ordinary people when he was able to do this, when he was able to identify animals and put them within not only a genus, but within an exact species on a map based on one single part of anatomy. It seemed to show incredible power, orderliness to nature. This wasn't just someone making up a scheme about pistils or stamens or something like that. This was really an ability to kind of understand nature at almost every level. So there's an incredible, kind of impressive power to that. And then last thing, we'll end on this point, then we'll have our break. This work is really important for laying the foundation for Darwin, who would come upon later. Organizing all of nature into these families, classes, orders, genuses, species, or genera species. It not only maps out nature in terms of order, but it creates the foundation for Darwin to come along and say, let's think about this a little bit differently. What if what we're looking at is not the map of God's creation, but instead a family tree? So this is one of the most, there's only one image in the origins of species, and this is the tree that Darwin drew to kind of show the idea that what we're looking at in taxonomy is really genealogy. What we're studying with these different animals as we place these into the categories. Why is a whale potentially sharing these internal anatomical similarities to mammals? It's because whales were probably mammals that moved into the water millions and millions of years ago. So in this diagram, each one of these lines represents 1,000 generations. So this is big time being organized on this graph. And he's showing how it can potentially branch out and develop all these alternative species. So again, a lot of scholars that study Darwin himself would say you can't get to the idea of evolution without having mapped out all of these categories and having surprisingly drawn connections between animals that don't on the surface look alike. here from different areas. So classification kind of revealed a really interesting structure that allowed, now it took a lot of imaginatively, but allowed Darwin to kind of bring us into a very different even world, this idea about evolution here. So we'll stop here, and then when we come back, we'll talk about the public's response to this, like popular, yes, exactly.
Thank you for coming back, and now we'll continue with Mike Guenther and Science and Society from Newton to Darwin. Mike?
To have a cat.
Okay, so we have in the 18th century this, powerful systems, starting with Linnaeus and then being adopted. And even though things have changed over years, the basic structure of the Linnaeus system about binomial nomenclature, the very structure of kingdoms, order, families, all those kinds of things have stayed in place, even when there's been internal revolutions about the actual way to categorize them. So Cuvier and others suggest new, more natural methods based on internal anatomy, and those are kind of folded into the system as well. But it does have, like I said, a lot of public prestige. I think if you were to kind of poll people in the 18th century or the early 19th century and ask how they interacted with natural science, one of the most popular venues was in this field of natural history. So I just want to talk a little bit about some of the places where popular culture and scientific culture kind of intersected. So one of the really interesting places are natural history museums themselves, which can kind of range all over the map. They're part entertainment. There's a little bit of P.T. Barnum-like showmanship involved with people like, this is Charles Wilson Peale here, who had a famous museum called Peale's American Museum in Philadelphia. There were other similar museums in most kind of metropolitan areas by the early 19th century in America, Western Europe, and in different colonies in Central and South America. And so these were places that were designed to entertain people, to provide especially popular, what they would call rational amusement or entertainment. So you have a growing group of people that often have free time, a rising kind of middle class in different groups. And I do think actually one of the other things to keep in mind is that the intense desire to find order in nature happens at a moment of intense change, when the orders of class, the orders of the traditional society are breaking down because of the Industrial Revolution. So, not to be a psychologist, not to put these people on armchairs and kind of psychoanalyze them, but I do think that there is this fundamental link, that they're intensely looking for order in nature because around them the order is changing so fast. The social order, boundaries, traditional ways of organizing people, society are kind of changing and in flux. And one of the groups, especially the kind of middle class that is emerging in the 18th and 19th century, are looking for ways to spend free time, to entertain themselves, but also to be edified and to learn. So you have a host of new venues, lecture halls, assembly rooms, natural history museums. I'll talk about botanical gardens in a second. These are places where you can be entertained, edified. It's pious, you're studying creation. What's more pious than studying God's work? So they have a lot of kind of cultural currents kind of converging on them. And Peale's Museum, now he's just kind of teasing us here, lifting up the curtain in this painting they did. But Peale's Museum, like others, are very interesting because they insist on organizing all the animals, the plants, the minerals under these new classificatory schemes. So if you go into a natural history museum, there's another one in England, what you find is everything in perfect order, kind of listed. They always insist on having tags so that you can read these Latin names, and you get to see the new order being revealed by naturalists and others. And so when you read accounts and letters, and especially newspaper descriptions, people talk about what it's like to see all of creation, all encompassed in one room, all organized and ordered in this kind of way. So for a lot of people, it was this really dramatic experience here. And one of the things, maybe this is a good point to talk about how there was also some confusion and some surprise at the new order that was being created. So let me just say a word about this class of mammals here. There are two things that Linnaeus and later taxonomists like Cuvier do that are surprising to people. One is that they put humans into the categories with other animals. They had always been in a separate category. So Linnaeus, in his first edition of the Systemae Naturae, puts people in the category of quadrupeds. He basically says we're four-footed animals that walk on two, and we don't have as much hair, but we're basically quadrupeds. And he gets that generates kind of a lot of controversy. But in later editions, he decides to actually get rid of the category of quadrupeds, which is one of the most ancient categories. It goes back to Aristotle, and it organized the way Westerners thought about animals for two millennia. And instead he proposes this new category of mammalia, of mammals here. And these are animals that are warm-blooded, that reproduce without eggs, that reproduce, and especially that nurse their young with mammary glands on the breast. And so this is a really interesting moment in Western history, one that generates controversy, because on the first hand, people kind of accused Linnaeus of being a little provocative, right? Because he introduced a sexual system of classification of plants. It's artificial because he said plants have male and female reproductive organs, and we're going to organize all the plants based on male statements. We're just going to count them. So that was seen as a little piquant at the time. And there's interesting kind of controversies about whether or not. It's luckily in Latin, so children can't read it. There's this question about Erasmus Darwin writes a famous poem, The Love of Plants, here, and it kind of takes this into a different realm. So this was a bit of controversy, and scholars are really interested in the way it represents kind of ideas about heterosexuality and about gender, the kind of norms of the 18th century that are under a lot of dispute during this time period and a lot of concern for people. And the other thing is, we find out when you look at his private writings that Linnaeus is very concerned with wet nursing, as are a lot of educated, enlightened figures in the 18th century. There had been a tradition in Europe of people putting their children out to wet nursing, not nursing children themselves. And this is increasingly seen in the mid-18th century as kind of unnatural. And so Linnaeus writes pamphlets against it. He's kind of concerned with these debates. And so, again, people are very interested, scholars, about where this class of mammals comes from. It does have a scientific basis in the sense that you can group animals by whether or not they breastfeed their young, but you can do it with dozens of other categories. So why does science choose in the mid-18th century to create a whole new category based on breastfeeding and stuff? And so there's a lot of gender politics involved in this, and then again, it becomes very controversial at the time people reflect on this. And I think there's a deeper lesson to be learned, which is science, using this new name of systematics, kind of claims that it can provide an objective classification that reveals the real order of nature. Right? That's a powerful claim to make at the time. But when you look very carefully at the categories it chooses, I'm not going to say that they're whimsical or that they're completely biased, but they reflect very pressing concerns of the people who created them. They're not necessarily objective here. They're responding to their very pressing ideas and concerns. And so I just want you to keep that in mind as we move along and I start to talk a little bit more about how science gets applied to race and gender, the kind of classification of races and people. You keep in mind this idea that there is a tension, that it's becoming increasingly popular and objective in popular imagination, the prestige of science, of classification. And yet when you look down very carefully at the categories it's creating, they seem to reflect very much the gender and class politics of the time period here. In a way that I'll show you actually came up in a court trial. It's really interesting. But I did also want to mention just a kind of a similar example, botanical gardens. It's one of the rages of the late 18th, early 19th century. People went to botanical gardens. You would buy memberships, and so you could take walks and strolls with your family to them. And a little bit like the Natural History Museum, they're not a place that you just visit once. They're kind of full-service centers of enlightenment in some sense. So botanical gardens usually have special houses created, greenhouses for growing plants and whatnot, but they also have libraries. Almost every botanical garden has a library, and by buying a membership or buying a ticket, you get to use the library. They always have lectures, so there's kind of an event schedule. Every day there's a lecture, a demonstration that's going on here. You have the right sometimes to pick some plants, which is very contested. If you give enough money, like if you get into the donor circle, you can sometimes get extra plants, things like that. But they're really interesting places where, again, the rising polite classes, the middle class, the upper class, start to kind of create an image of themselves as being enlightened people who, rather than going to taverns or pubs or even sometimes dancing, they've got these new forms of rational entertainment. And when you go to a botanical garden, you can't help but be struck by the order in them. These botanical gardens are laid out in these incredibly geometric orders, but unlike the Renaissance period, which also had geometric gardens, these are all laid out in a taxonomic schemes here. So you have them all laid out, usually the Linnaean system, but sometimes it might be a different one. But you have these, you get to see all of creation kind of a microcosm, organized in a very orderly fashion here. There was one great account where people said it was like being in Noah's Ark, but for plants. Just 2 by 2, all of God's creation kind of gathered here. Again, a powerful way in which, in the public imagination, this idea that there is an order of nature, and that science and classification are the way to reveal that order takes place. And you could multiply this. There are many other kind of examples of different types of museums and places. But if I had to pick 2 places to watch science and society interact in the early 19th century, I would pick botanical gardens and museums, because they're just really fascinating places. They did intersect in one really interesting way in a courthouse as well. There's a case that historians of science have long known about and that they find fascinating. It's a New York case called Maurice versus Judd. And the basic question of the case is a whale a fish or a mammal? Now, why would that be a legal case? It turned out that there was a very shrewd whale oil merchant who decided that he shouldn't have to pay the New York tax on fish oil because a whale isn't a fish. Right? So that's what Cuvier, Linnaeus, and others had said. And so they went to court over this here, and they brought in the kind of the big guns of the American Enlightenment, people like Samuel Mitchell, who was a New York philosopher, and in his day would have been equivalent to someone like Jefferson or Franklin, widely known all throughout America. He testified along with other famous scientists on behalf of plaintiffs here. And I have to say that court trials are really fascinating for historians of science, in this period, but in every period, because when you bring science before the bar, you get cross-examination. You have attorneys ask, well, how do you really know this? Why do you have the class mammal? How do you? So otherwise, it's kind of like this immense deconstruction. Science often kind of exists in a black box. It just produces knowledge. We don't know where it came from. But when it gets in front of the bar and is cross-examined, it has to explain every detail of the chain of custody, what its ideas, what its theories are. So, and this is especially during the 20th century when you have fingerprints, DNA, all these fields. If you want to understand the workings of science, sometimes legal trials are the best ways to see if you can't get access to the notes or notebooks of scientists. So this was a huge cause célèbre, and all the newspapers covered it in America. They covered it all throughout Europe, and it hinged around this class of mammals, and this idea of why should a whale be considered a mammal as opposed to a fish, and they pitted different groups that had different claims to authority. So they called in all these, the defense called in all these different whaling captains and sailors and asked them, is a whale a fish or a mammal? They said it's a fish, right? It swims in the sea. And interestingly enough, they pitted science against the Bible at the trial in ways that normally didn't happen. Normally science and Christianity, everywhere except for France, seemed to kind of go together. The French Enlightenment took a lot of the French philosophers were opposed to what they saw as corrupt Christianity. And so in France, there's a lot of potential conflict between science and religion, but in most of the rest of Western Europe and America, the two were seen as kind of handmaidens. They went together. Science exposed God's divine plan. So they pointed back, the defense said the Bible tells us the proper classification. Genesis says, birds of the air, fish of the sea, beasts of the land, or the cattle that creep, all that creepeth on the land. It's my favorite category, the creepeths. Those things that creep on the land. And so they pitted this. They pitted multiple authorities. So the Bible gives us a clear taxonomy. Common sense gives us that clear taxonomy. Let's bring in all these different sea captains. And then they brought in manufacturers, the people who actually made whale oil and fish oil, and said, is there a difference? When you make cod liver oil, and when you make oil from fish, is there a fundamental difference between that and whales? And so they pitted all these different groups, and they asked the jury to decide, who are you going to believe? The new philosophy with this kind of slightly risque category of mammals, and with this kind of dissecting type thing, or are you going to believe common sense, the Bible, merchants, and others? And so it ended up being, like I said, it's a really interesting kind of case. And I will provide, Joanna mentioned bringing a bibliography of kind of readings. I'll provide at next week's section a listing for anyone that's interested in kind of engaging readings about the history of science that are connected to this class. There is a book called Trying Leviathan that is about this court case. That's a really interesting read here. So not to string this along, but so the jury goes out for 15 minutes. But I'll wait. Did you want to ask a question?
I don't know what the outcome of it.
Okay, yeah, what is the outcome? Exactly. I'm stringing this along. So, So the outcome of the trial is the jury goes out for 15 minutes and returns a verdict that the whale is a fish. And this generates really interesting commentary all around the kind of Republic of Letters. So some people decry it as kind of Philistinism and science under attack. Other people say that there's good reasons. This is a victory of common sense over common sense in Christianity over natural philosophy. And then the New York legislature goes back and rewrites its statute to make it even clearer so that this won't happen again, to include whales and others here. But so yeah, the short answer is, at this moment, the science of taxonomy loses. And I think there's an interesting way in which there's both a public embrace of the new order of taxonomy in botanical gardens and museums, and as I showed a little bit earlier, among artists that are interested in getting a deeper glimpse into the structure of skies, clouds, nature. So on the one hand, there's a popular public embrace of all of this information and classification, but there is also a popular pushback here, whether we're talking about this system or even later a little bit with Darwin and others. There are people that are perfectly willing to reject what science says about classifications when they go against what seems like common sense or long-standing tradition here. So this is one in which science kind of loses here. Let me turn in the last section to talk about the way in which, because science offers this powerful tool of classification, people intensely use and appropriate it in order to settle what are some of the pressing questions of the day. Are there different races of people? Are men and women fundamentally, biologically different? These are questions that have existed throughout different parts of history, but they're intensely debated in the 18th and 19th century as the slave trade is debated, as global imperialism brings different groups of people together. And so people have these long-standing questions, and science comes along and says, well, we have the tools to answer them. We know how to objectively categorize things. And so I want to talk about some of the different ways in which the science of categorization and classification get extended into the social sphere. So one of them, just sticking to the American example here, is there's a whole, what they call the American School of Craniometry. It's a new kind of science that studies the size and shape of skulls here in order to kind of understand this deeper question of, are there racial differences between groups here? And so there's a individual named Samuel Morton in Philadelphia who collects, I can't remember the number now, several hundred skulls, mostly Native American. He has this giant kind of collection here. And he develops these kind of techniques about measuring. But again, what's really important is that you can measure a lot of different things. You can create a bunch of numbers, but without the categories or the classification, the rules, you have to have a set of objective rules that allow you to structure whether one skull is in a category or not. And that's what scientists start providing with all of this kind of scientific study of skulls. There's a lot of debate about whether this is good science, bad science. I don't mean in a moral way, but there's a question about whether the science itself is perfectly objective. It just was being used in ways that we today would find morally objectionable. So you could perfectly say that the end result of most of these studies is that there's a ranking of the size of heads, with Europeans on top, and then other different races going down to the bottom. The question is whether that's true, but it doesn't mean anything, because obviously head size doesn't necessarily mean anything, necessarily. Or is it actually bad science, like that if you measure skulls, you will not actually get this result if you do it objectively. So this was an issue that the evolutionary biologist Stephen Jay Gould, I don't know if anyone's heard of him, he was kind of a popular writer. This was something that he took up later in his life. He spent about 15 years collecting all these skulls and remeasuring them, doing these things. Because you could try to, and they tried to develop these set rules for how to kind of measure the angle of skulls, the size, or develop a kind of shot technique where you take gunshot little balls and would fill the cranium with them to figure out how many could fit in there to get it volume here. And so Stephen Jay Gould had like people reconstruct the shot, and he would measure all these skulls and kind of do things. His argument is that the math and the science is actually bad as well. That if you actually do these numbers, these skulls together, that you won't get those numbers. And more importantly, skull size, brain size, the different kind of proxies that people are using to categorize, they vary so widely within groups of people that it doesn't make any sense necessarily, one could argue, to lump groups together. So you take a skull of a 13-year-old, right, and compare it to the skull of a 30-year-old. That's obviously a ridiculous comparison. But there are similar things that affect it. The brain size for people who die by different diseases is dramatically different. Stuff like that. So within each of these things, I mean, I guess what I'm trying to get at is that what you see as the 19th century is so obsessed, and I think that's a fair word to use, so obsessed with classifying into groups that they miss sight of the fact that there's just such wide diversity within groups here. But these studies get, repeated in newspapers, periodicals. It's given the imprimatur of science itself, that this is objective knowledge, and so it plays into these public debates. It has a real big impact. Another field, there are literally dozens of these fields in which new techniques of classification, combined sometimes with measurement, give us new order in the human world, is what people are saying. So one of them is anthropometry, which this Frenchman Guenther develops here. This is his kind of chart of how he's going to measure people in all these very intense ways. There seems to be kind of two goals. One is to create, and he's the person that kind of invents, in some ways, mugshots and specific identification cards. He thinks that you can identify any individual if you have these precise measurements. So this is a kind of rival of fingerprints, right? So how do you know someone is who they say they are? You take a certain set of these exact measurements, and you can know who they are. Right? So that's one potentially interesting use of this scheme. The other use is you can start to classify people into groups. What if all criminals share the same anthropometric measurements? Or what if all people that he actually creates this term or uses this category of dullards, people who are just mentally slow. What if they share the same thing? So there's this intense desire to find different groupings here. And with photography coming along in the mid-19th century, that also gets incorporated into these kind of programs here. So this is one of Guenther's charts for identifying like the different ears, noses. Maybe move on to this one. How you can identify groups of people: the criminal, the forger, the liar, the drunkard, all these different categories based on the distinctive ear patterns that people have. Having measured thousands and thousands of ears, he starts to argue that I can tell, a little like Cuvier, who says, give me a tooth, I'll tell you what you have. But Tillon's like, give me an ear, I'll tell you what kind of person you have. Right? This order here. So go back to it there. He tries it with all kinds of things, noses, cheeks. He basically, as this kind of diagram indicates, he divides the face up into a classificatory scheme of these different elements: nose, brow, cheek, things like that. It decides that not only can you identify the individual, but you can identify the group that the individual belongs to. And so this becomes really powerful information, powerful ideas that shape the public's impression of criminals, of peniology, punishment of people. I will say that it can be balanced out by other groups of people using science in different ways. So there's the famous statistician Quetelet, who's a Belgian statistician. He runs through all the numbers of the census, which is maybe one of the greatest mergers of classification and numbers we've ever seen. So the census is based on creating a very orderly classificatory scheme of people and information, and then it gathers millions of entries and helps us see the pattern of society in terms of births and deaths, in terms of education, movement. So we can kind of see the order behind society in interesting ways. And Quetelet, when he's looking at that, discovers that year after year you can predict how many people will commit forgery. I mean, he says, how is that possible? How is there a predictable element to the numbers of crime when every crime is such an idiosyncratic decision and effective? So his argument, he starts to take a kind of radical moral posture, which is maybe we shouldn't be blaming criminals. Maybe it's society that creates the crime. Otherwise, crime is a social phenomenon. It doesn't matter who the person is. We're going to have a certain number of murders. We're going to have a certain number of burglaries. And he starts arguing, he starts one of the first campaigns to abolish the death penalty, as far as an international, grounds it in science and classification. So I just pointed out by saying that not all science is creepy, use of classification. Sometimes when I teach this on campus with students, it's a little overwhelming to read craniometry, anthropometry, all these different things. It seems like science is engaged in this, in the 19th century, in this attempt to, like surveillance and organizing society, justifying all forms of discrimination. And I don't want to paint that bleak of a picture. It is a powerful tool. For those that want to legitimize discrimination, it becomes the most powerful tool in their arsenal here. But it also can be used by other groups to kind of justify more equitable treatment of people. Using on this theme again of kind of photography, Francis Galton, who's one of these key figures in statistics and classification. I mentioned him a little bit earlier with fingerprints. He decides to do composite photography. So he takes thousands of photographs of different groups of people, again, criminals, different groups, or even like wealthy people. He has a whole category of brilliant scientists like himself. Where he takes all their pictures and then starts to try to merge them together with composite photography. So you get the idealized image. What does the perfect, so these are larceny. Here's burglary. So what does a burglar look like? This is an image of 7 people. Composite, this one's a composite of 4. He has these different ones for different groups here. So they start using new techniques of photography to kind of organize people into these kind of patterns here. And I could go on with different examples of this, but I think you probably get a clear sense of the pattern here, right, of the order behind it. The science of classification over this period of the 18th and 19th century is used as a powerful tool to understand all different aspects of the natural world, and is used even increasingly to try to understand the human world. But at the heart of it, often the question to ask is kind of, why do you put one set of things or people into a category here? And when you ask this question, whether it's a legal trial, or you ask in this group, like, why would you put together different races or genders or different groups of people? Often science doesn't have exactly the most objective answer to say. A lot of social prejudices, a lot of personal assumptions get embedded into these categories, especially when applied in the social world here. And you see in the 20th century, in some ways, a kind of move away from this. Although in other fields like psychology, like the diagnostic manual, and we do use classification in a lot of other fields here. So like any tool of science, it can be a very useful tool. It can also be abused, be used in ways that we feel could be very morally questionable. So that's kind of what I wanted to say about the topic. But we have some time left over, so we can go through some questions. Yeah?
If you are even subtly predisposed to an answer, can you not just create science to support that theory?
So
Or
the
not
question,
create science, but find the science to support that theory.
so let me rephrase. So the question is can you, if you have a predisposition to a certain outcome or theory, that you think a certain way about groups, is there anything to stop you from just opposing that? Kind of how plastic is classification?
Yeah.
So it depends on the field. There are some fields where you'll get pushback from people, other scientists who might expose that your categories don't work. But in general, there's a lot. I mean, I think when you look at a lot of these different examples, you'll see that there was a lot of room for personal opinion and ideas to shape the categories here. But there are definitely some fields in which there were pushback. Yeah.
You gave an example, an illustration, a painting that you said seemed to convey that when the taxonomy of clouds was produced, that the amount of detail in the visual art changed. Mm-hmm. In your examination of other fields, say music or taste, did cuisines taste after they had a taxonomy? Did music seem to change after they developed a taxonomy? And in fact, are there taxonomies for those other fields?
Okay, great question. So the question is, I've been given this example of how the visual kind of culture display of clouds or rocks changed in light of scientific taxonomies in those fields. So were there parallel taxonomies in food, music, and other areas, and did those shape the way society understood those fields? Is that a fair kind of thing? So yeah, I think that's a great question. Trying to think here, maybe Eric can help me out as far as music, not to put it in the spot, but there's definitely a way in which to appreciate any subject matter, understanding, the term that's used in the 18th century and 19th century is analysis, is another term, systematic. So what all of these fields are doing is trying to take a complex subject and saying, we're going to break it down into its core elements and understand how they're related to one another, right? So there's a sense in which if you now understand and see a topic through that prism, you're going to see it kind of differently. So, and Eric's going to answer about music. I'm trying to think about
Sure. One thing I would say is, because the music taxonomy and the sort of approach to it, as with most fields, music is late in the development. The
Right.
Romantic era is well after the Romantic era in arts and such, so it comes later in the 19th century. But the prime example would be in the 20th century, after Arnold Schoenberg and friends create the 12-tone system, that throughout the early and mid-20th century, you have people who have taken the analysis of that and turned it into their compositional process. So they take the mathematical formula that were used to analyze that kind of music, and they start composing using those examples. I would think that would be a classic example of the taxonomy becoming the driving force in the community.
Yeah, the music, yeah. And then in mathematics, there's the development of group theory, which is very complicated, but it's basically about, it's not even about numbers, it's about explaining symmetry, and it's the most rigorous form of how do you organize things into a meaningful group that share the same properties. And there's a whole field of mathematical group theory. That gets applied to dance, to music, to other fields. So there's some, but I don't think that goes into the popular way, the way the clouds did. I don't know about food. So the short answer is it's a good question, and I'm not quite as sure about those particular fields, music or food. But there are definitely a lot of other fields, the study of diseases, other things like that. But yeah, I don't know as much about food, but I'll try to look into that and see, because I don't know if there was a food taxonomy. Yeah.
My question is about fingerprints
Okay.
in identical twins. Are the fingerprints still different?
So the question and I'll start off by saying that my knowledge of fingerprinting is kind of limited, unfortunately. But so the question was, are identical twins, do they share the same fingerprints? I hear some people kind of confidently saying that they do not. I don't know. So the answer is I don't know, but other people are saying that they have heard that they do not share the same. I mean, one of the things that's interesting is, and again, I mentioned about trials, is these kinds of systems of classifying fingerprints, all these. If you ever watch a trial, like the FBI has like systems of classification for tire prints, and you can take almost anything and kind of break it down into an orderly classification scheme. And there's someone that's writing a big book on the history of forensic science. It's coming out. And I don't know what they'll say about this, but my understanding is that it's based on statistical inference. We don't know always. There's no exactly certain way to know that people don't have the same fingerprint. What we have is statistical arguments that say it's this unlikely, right? So whenever you have a trial, someone will say that it's a 0.0005 chance or something. But I don't know. Maybe I'll look up online and see what they say about identicals. But these are questions that people ask all the time. Yeah, like nature has really interesting anomalies that kind of get in the way of any good system.
To push that even further, I've read or seen something fairly recently that talked about cloning,
Okay.
which pushes the identical twins the next step. Even there, the fingerprints were different.
Were they? Okay.
The factors which came to the classification.
And, that's interesting. So the question / comment, or more a comment about how in cloning it's even been argued that identical twins would have different fingerprints. I know that one of the first steps after they started classifying fingerprints is to ask, are there reasons why people have different fingerprints? Could it be environmental, or they didn't have the language of genetics or the ideas, but classification often opens up questions as people try to answer these.
Isn't the same thing true of DNA? Even if you have identical twins, the DNA is somewhat similar, but there's still a difference.
So the question is, again, I have to go to the jury here, about, is DNA, would it be identical if people, even among twins? I see you raising a hand, yeah?
New York Times says that identical twins do not have the same fingerprints, but they have the same DNA according to a standard DNA test.
Okay. So, okay, so maybe more advanced tests could potentially statistically identify some differences. So, I love smartphones. You have to look at
You talked about how the classification makes it easier to understand science. Can you give us a feeling to what extent those classifications may inhibit an understanding of what nature's really about or what nature's really like?
Yeah, that's a good question. So I've been talking a lot about how classification is useful to science, how it is useful in terms of discoveries, in terms of letting people communicate, and that society sees it, whether we like it or not, society sees it as a useful tool for understanding its own order, right? So that's the big theme. In what ways is classification not useful or helpful? Can it lock us into seeing the world in certain patterns that are not helpful, right?
Right.
And I think obviously in these social and moral examples, it becomes kind of clear. But even in the scientific examples, there are, and there have been a lot of scientists that have reflected on this, that you can get locked into the categories of your own thought and you can miss examples. Here, Fermi, who was one of the famous particle physicists, he bombarded an atom and kind of released certain radiation. He didn't understand what he was doing. And in fact, he covered his instrument with tinfoil because it was giving the wrong readings. But I bring up this example because he was making advanced discoveries potentially in physics, but he did not have the conceptual framework to know what was happening. He just thought his instrument was misbehaving, and so he just wrapped it in tinfoil. This was like in the late 1930s. So there are definitely examples. So the standard model of physics is other fields in which the categories by which people are processing new data are so kind of firm that what could be a potential discovery, they just say is an anomaly, it's an accident, I must need to rejigger my equipment. So there's some examples. Astronomy is the same way, the debate about whether Pluto is a planet or not. I mean, there's all these different kind of things in which there are serious debates.
Global warming.
Global warming, is that a
Yeah.
thing or not? And a lot of that depends on having certain classifications as far as the other stuff. Yeah, so there are different examples. Fermi comes to mind as one. Yeah.
Well, I had two examples. One is the nature of ulcers.
Okay.
You know, and I won't go into that. The other I find more interesting is what's called cold fusion. There's no theory that explains what the scientists that have been working with it have been experiencing, and so it's being rejected.
Okay.
And I just wonder, it seemed to me that the lack of a classification system really is inhibiting, but on the other hand, maybe that's what's needed in order to further it when the time comes.
Okay, so you mentioned the example of cold fusion as an idea that if there's not a theoretical framework to explain it, that it makes it a hard time for people to accept it and work it in. So I think that the more you get into the specifics of a field, I think the more examples you'd find where a framework, the lack of it makes it hard for you to develop ideas. It's kind of like a grammar of science. If you don't have that grammar, you can't put together certain sentences.
The problem
Yeah.
in cold fusion is it's so difficult to reproduce results.
So experimentally, the problem with cold fusion is it's hard to produce the results. So
It's to repeat the results.
Because they don't understand the...
Well, no, it's
Period.
just that you get 5 people doing the same experiment and they all get different answers, and nobody understands why.
okay. Why they get those different answers here. I mean, I think one of the bedrock assumptions behind all of these schemes and behind, I think, science itself is that you expect an orderly, predictable nature. Einstein famously said that God doesn't play dice with the universe. Right? We expect nature to give us the same response if we do the right methods. Or we expect the classification scheme will reveal the hidden order of the natural world. So there's a fundamental leap of faith that all science kind of takes with it. And as we're suggesting in the examples, bring up a good one. So in some ways, it can be a very useful framework for everyone to share, to do a collective enterprise, to understand nature. And other times, it can lead to blind spots, or it can lead to, without a framework, without categories, it's hard to do science. So, one last question.
It would seem like the fundamental need is to solve problems. And as you look at those things, the more categories that you can develop, the more likely you can find the patterns that are useful. Has there been any kind of consideration of comparison of the complications of linguistics, like one language to another?
Linguistics is another field that developed a whole classificatory scheme to make it a science out of a language here. But I don't know. I'd have to ask my colleagues, like Cynthia Hansen, about whether or not the tools of linguistics are used to diagnose whether or not particular scientific fields. There are linguists who study science, and study the language within every particular science. I don't know what their results are, but I think the first part that you mentioned is definitely an interesting, probably a great note to end on, which is that the more you map out these classification schemes, the more you raise potential areas of research, questions. I think the idea of thinking of classification as a map, how to map out what we know, what we don't know, is potentially useful. And if a topic is off the map, that's problematic, right? It's hard to think outside of the map itself. So we'll end there. And then the last lecture next week, we'll talk about visualization, science and the way it uses imagery.
Thank you very much, Mike. If you have filled out the registration for JR's course, you can leave it on the table here or put it on the table in the hallway. And remember to turn your cell phones back on, and we will see you here next week.